Well, hello, and thank you for joining us this morning. I want to welcome you to Hydric Soil Indicator Insights with Hammer Environmental. Our subject for the next hour is general guidance for using the field indicators of hydric soils in the United States, version 9.2. We are thrilled to have over 140 people who signed up for today's session. And as you can see from the map on your screen, we have participants joining us from across the globe. While most of you are calling in from Virginia, we also have attendees from Georgia, Ohio, Pennsylvania, Maryland, Florida, North Carolina, and even as far away as Canada, India, and Nigeria. So welcome to all of you. I'm so glad you're here. Before we dive in, a few quick housekeeping items. You'll notice we've muted everyone's microphones. With this many participants, keeping microphones off will help us stay on track and get through all the material we've planned for you today. If you have questions or comments along the way, please use the Q&A feature. Here's a helpful tip. At the bottom right of each slide, you'll see a slide number. On this particular one, that's just a hashtag. If you can reference that number when you submit your question, it'll make it much easier for us to provide context when we respond. So we'll be monitoring that Q&A throughout the session, and we will do our best to try to address questions as time allows. Finally, a PDF copy of this presentation, along with other resources we'll mention today, are available on our website at hammerenv.com under Educational Materials and Resources. So my name is Greg Hammer. I am a retired United States Department of Agriculture, Natural Resources, Conservation Service soil scientist. Before we begin, I want to clarify my background and perspective so that you know exactly what you're getting today. I am not a researcher. I am not a professor. While I have tremendous respect for those who serve in those roles, that's not the lens through which I approach this subject. I am a hydric soil practitioner, which is really a fancy way of saying I've spent a lot of time with wet feet and a shovel in my hand. I spent 30 years with the U.S. federal government, and I'm simplifying this significantly, but my main two tasks over those 3 decades were making soil surveys and conducting wetland delineations for Food Security Act purposes. So now that I retired from USDA, I'm the owner of Hammer Environmental, where my main focus is passing on what I've learned after digging and describing literally tens of thousands of soil observations and completing over 3,000 wetland delineations. Because of my practitioner background, I'm going to assume at this point that you have at least some basic working knowledge of the field indicators of hydric soils. And my focus today will be on practical guidance, the kind that matters when you're really out there, literally shedding blood, sweat, and tears. This webinar today is being presented as a result of a partnership between Hammer Environmental and the Virginia Association of Wetland Professionals. And let me just say that this partnership reflects a shared commitment to advancing the quality and consistency of wetland delineations throughout Virginia and beyond. And through collaborative soil science training with a focus on hydric soils, we're working together to strengthen the technical foundation that supports sound wetland assessments across the region and beyond. I'm grateful for the association's continued support and look forward to expanding our collaborative efforts to serve the wetland professional community together. All right, field indicators of hydric soils 9.2, let's get going. So let me just start with the obvious. If you're using any other version, you should stop immediately and start using the most current version. A digital copy of 9.2 can be downloaded at the link displayed. A hard copy of 9.0 is available for free by sending a request to the NRCS Distribution Center. Now, based on past experience, NRCS will run out of hard copies at some point, and when they're gone, they're normally gone. And they don't normally print again until they get a new version, which would be 10.0. Which I don't anticipate in the near future. If you value having a hard copy on the shelf or in your hands, My suggestion is do not wait. Order your copy or copies today. They are free and you can order as many as you need. There are errata sheets that have been issued. I'm not going to go through all of the changes line by line or word by word. I would encourage you to do that on your own. Let me just characterize the changes so far this way. In my opinion, there's no significant changes that are likely to make much of an impact on your decisions in the field. Generally, the errata up to this point reflect wording changes that were made to improve understanding and consistency throughout the document. I will tell you, though, that when I was preparing for this webinar, I noticed a couple of more items that needed to be updated. And I did report those to the National Technical Committee on Hydric Soils, and they did respond and were appreciative and indicated that errata 9.3 will be coming soon. Okay, so what's new in version 9 or 9.2 from from version 8? So there's a new indicator, A18 iron monosulfides. Notice that the indicator is for use in all land resource regions, so the entire country. I will tell you a lot of times when I talk about indicators, and sometimes to my own detriment, I often restrict my thinking to my own experience or region of the country that I'm most familiar with, which is the Mid-Atlantic. So in the Mid-Atlantic region, where most of you on this call are located and work, the principal location for this indicator will be in coastal marshes or dredged materials. But just know that there are other environments that this indicator can form in. Most often, this indicator is going to be in extremely reduced environments, and there is a darkening of the soil that is not caused by organic matter, but instead is caused by iron monosulfides. So these soils have been problematic in the sense that there is a known history of extreme wetness, but because of the environment that they form in, the typical redox features don't form or they are masked because of the darkness of the iron monosulfides. So there is a field guide in the glossary in the back of the book that provides guidance on determining the presence of iron monosulfides in the soils. The methodology of having a positive hydric soil indicator is different for A18 than all other indicators because it requires at least 2 separate observations, and there are 3 different ways this can be confirmed in the field. It starts with a moist color requirement of value of less than or equal to 4 and chroma of less than or equal to 1. There is no percent requirement, only that these colors are present in the upper 10 inches. There's an oxidation test that can be done in 2 different ways. The quickest is to apply a 3% solution of hydrogen peroxide, which is just over-the-counter peroxide, and after 10 seconds, you see an increase in the Munsell value. Or you can expose the soil to air, and you see this same change in color occur between 30 and 60 minutes. There's no measured color shift threshold other than the value goes up, meaning it gets lighter in color. The third method for testing the presence of iron monosulfides is to put freshly exposed soil sample in a plastic bag, add 3 to 5 drops of hydrochloric acid solution, seal the bag, wait 1 or 2 minutes, and then do as pictured here on the right, you do the whiff test. Do you smell hydrogen sulfide, that rotten egg odor? All right, so what else is new? So test indicator TS7 in version 8 is now S12, in version 9. It moved from test indicator status to fully supporting a indicator. So this indicator was established to help identify hydric soils in the swale portion of the dune and swale complexes of barrier islands. So prior to the development of this indicator in these dune swale locations, the previous set of indicators did not always manifest themselves, even in known areas that met the technical standard for hydric soils. The National Technical Committee for Hydric Soils also considers it worthy of further study in other coastal areas outside of that current barrier island requirement. Another new change is that test indicator A6 from version 8 is now A17 mesic spodic. I will tell you that I'm not personally familiar with this indicator as it's restricted to a few major land resource areas in New England. So unless you're working in that area, this indicator will not apply. But I do want to tell you a little background story to give some perspective about the effort that goes into developing hydric soil indicators. So back in 2004, there was a soil tour that was taking place on vernal pools in Rhode Island. And at that time, they were using version 3 of the field indicators. And there was no hydric soil indicators being met in what was a very obvious wetland. So this group of soil scientists in New England realized there was a problem. And then for the next 21 years, they stayed at it until finally this test indicator got approved. And the point in telling you that background story is that you will have some level of appreciation of the significant effort and high scientific bar that is set before an indicator makes it into this book. For this indicator A17, we open the pages, we read a couple paragraphs, we read a user note, and that's all that we see. But to get to that point, it took several persistent people working hard for over 20 years. So thank you to them and others who work so hard to make this a true science-based process. All right, so something else that's new in version 9 is that there was a test indicator. I'm going to call it a cleanup. The test indicator section has been removed and the test indicators have been reorganized. So there's some appendixes in the back of the book. Appendix 2 has test indicators that are listed by land resource region and major land resource area. And then in Appendix 3, there is a list of indicators that are no longer applicable and have been deleted. Okay, so that's the headlines of what's new. Let's move into some of the general guidance of version 9.2. So I'm stating the obvious here, but I think it's important to say that the field indicators of hydric soils is a field guide, and it is specifically made for on-site verification. So why does the field guide work so well? Indicators are soil morphological features that are a result of biogeochemical processes that take place under prolonged anaerobic conditions. So what does that mean, that phrase biogeochemical processes? Well, it's not just biology, and it's not just mineral earth, and it's not just chemistry. It's the chemical interaction between living organisms and the soil itself. The microbes drive the chemistry, and the chemistry creates the soil features that we observe in the field and use as indicators. These are often repeatable patterns of mostly color in the soil that are in conjunction with specific soil texture groups that confirm the soil in place meets the hydric soil definition. I also think it's worth mentioning that in the field indicators, the National Technical Committee for Hydric Soils wanted us to know some things, and they provided guidance on the field process and procedures. And here's what they tell us. They tell us to consider the overall site, not just what you're looking at right below your feet in the ground. They want us to understand how water moves in the site that we're working. So think about this. Why would the National Technical Committee on Hydric Soils tell us that, this as a part of the guidance? Well, the reason is because the committee, in essence, is reminding us to engage our brain and use common sense when we're making these decisions. Don't just be a checklist robot. Think about the bigger picture when you're making these decisions. We use three factors to determine a wetland: soil, plants, and hydrology. But ultimately, it's always about the water. Hydric soils are not born or deposited that way. They form in place through a set of processes. Something else I think is fantastic, but something else that the committee gives us in as guidance is that they tell us to dig a hole. And those of you who have been around me or know me know that I beat this drum over and over and over to dig a hole. It doesn't say get your auger out until sometimes you need it when you're going deeper, but the guidance is to dig. And I understand the efficiency of an auger, but sometimes you need to take the time to dig a hole. And the reason is because you get a much better view and understanding of what's actually happening in the ground as opposed to turning an auger and spilling out the soil on the ground. And then another general guidance they give us is to complete a profile description. And in order for you to be good at indicators, you have to know how to complete a soil description using horizonation. Okay, so one of the most important things to know about applying hydric soil indicators is knowing where to start your measurements. So sometimes you don't know the answer to that question until you've described the soil and considered specific indicators. Hydric soil indicators rely on looking at specific soil features at specific depths, often with specified thicknesses. So it's really important to know where you start your measurements is not always the same. So in this picture that we see here, the yellow line represents the organic soil surface. The green line represents the beginning of the muck or highly decomposed organic material. And the blue line represents the start of the mineral layer. The soil surface for field indicators A1, A2, A3, S2, and S3 begins at the actual surface or the yellow line. So for most of you who are on this call, A1, A2, A3 is are indicators in the all group that are very high in organic matter, as is S2 and S3. And S2 and S3 are used mostly out in the upper Midwest and western part of the United States. If you're in land resource regions W, X, and Y, which is Alaska, or R, which is New England, or you're considering two different indicators, F6, redox dark surface, and F7, depleted dark surface, which are present in the Mid-Atlantic region, measurements begin at the mineral soil surface. And that's the green line. Excuse me, the blue line. That's the blue line. And then for all other land resource regions and indicators, you begin your measurements at the muck, which is the green line, or the mineral surface, which is the blue line, whichever one starts first. So I understand, our audience here is broad, but I'm going to speak to the majority of the audience here and say this. In most situations, you're going to start at the beginning of the muck or mineral surface, whichever is first. And then just think about those other scenarios and situations if you're using some of the other indicators that are listed in the first, in the yellow and in the highlighted blue section. Okay, so I want to talk about some important indicator texture breaks on the mineral soil side. So the sandy or S indicators have layers that have a USDA texture of loamy fine sand and coarser. So if you look at the texture triangle here, all textures that follow into the yellow highlighted area qualify as having S or sandy indicator status. All textures that are white or uncolored fall into the F or fine or loamy soils category. Soil textures that are in blue can fall into either category. So let's talk about that. So in the loamy sand category, if it is a loamy fine sand or coarser, it's an S indicator. If it's a loamy very fine sand, then it goes to the F or the fine side. So what's the reason for this distinction between loamy fine sand going to the sandy side and loamy very fine sand going to the fine side? Because it would have been, in my opinion, a lot easier if the committee had just said, well, all loamy sands go this way or that way. But they didn't. Why? It's because, and it's about the difference in water retention. So very fine sand particles, which are 0.05 to 0.1 millimeters in size, behave like silts. They hold significantly more plant available water than a standard loamy sand. So for that reason, the loamy very fine sand soils form redox features more like the fine soils than the coarser soils do. So how do we make this separation in the field? It's good that we understand where the break is, but how do we do it in the field? So to drill down on this a little bit more, here's the actual guidance from the USDA Soil Survey Manual on that threshold criteria. If the dominant sand fraction is medium, you use no modifier. It's simply loamy sand. In the USDA system, medium is considered the standard reference point. Therefore, we only modify the name if the soil texture significantly deviates from that standard towards the finer side, fine or very fine, or the coarser side, which is not pictured because for S and F indicators, we want to focus on the line and how to distinguish these soils. Here are a few tips for distinguishing very fine sands from fine sands in the field. Notice the particle size difference in millimeters at the bottom of the chart. Fine sands clearly feel gritty. A very fine sand has a grit sensation, but is much softer. It feels like flour with a little grit in it. Fine sands are easy to see. You can see the individual grains, where a very fine sand particle is barely visible with the naked eye and looks small, like small tiny specks with a 10x hand lens. So sometimes you need to be able to not just texture the mineral fraction of the soil to use the indicators properly. You also need to be able to texture the amount of organic matter, or more specifically, the organic carbon content of the soil. There are several indicators that require you to be able to make a field estimate of the amount of organic carbon in the soil. And you need to be able to determine if the soil material is a muck or a mucky peat or a peat or a mucky mineral soil. And in order for us to be able to even have a chance at accomplishing this in the field, we have to know what these terms mean. So, soil taxonomy groups soils into three basic types based on how much organic material they contain. Specifically, how much organic carbon is in that organic material. There is a standard conversion factor that is 58% of organic matter is organic carbon. Now, obviously, that can be something that varies greatly, but that is the standard accepted conversion factor. So what that means is that roughly an organic soil that contains at least 20% organic matter will have 12% organic carbon. So organic soils are dominated by accumulated plant material and form in either cold or wet environments, giving them low density and high water holding capacity. Then mucky modified mineral soils contain enough decomposed organic matter to noticeably change the color and physical behavior of the mineral soil, and they contain 5 to 12% organic carbon. Some of you may remember that this used to have a sliding scale based on clay percentage, but that requirement was eliminated. And then the third category is mineral soils. And mineral soils have less than 5% organic carbon. So how do we make this distinction in the field between organic soil, mucky modified, and mineral soils? I will tell you, I think this is one of the harder things to do in the field, even for very experienced field soil scientists. So in the field indicators for hydric soils on page 3 and in the core regional supplements, there is guidance for making field estimates for determining organic content. And so what I've done here is I've adapted that same language from the indicators and the regional supplements, and I've made it into a flow chart. So I'm not going to have the time to go over this in detail, but I want you to know that this is a reference that is available for you that you can get from the Hammer Environmental website. So texturing soils in the field, whether it's to determine sand, silt, and clay content on the mineral side or organic carbon content on the organic side, is a very valuable and important skill to be effective at applying indicators. And just like anything else that you do in life, without practice, you don't improve your skills. So one of the things that I'm suggesting, one of the things that I do that really, really helps me, and you may want to consider, is I keep samples that I have lab data on to use as a reference. And I do this for mineral textures and for organic carbon content so that I can use those to help sharpen my skills in the field. Okay, so once you have determined that you do have organic soil materials, you then need to know what kind of organic material is it. So there are 3 different distinctions based on levels of decomposition. The first is peat. It's also called fibric material. It's coming from the word fibrous, and this is organic matter that is slightly decomposed. Think of recognizable dead leaves and litter. Then the next level of decomposition is mucky peat, also called hemic material from the Greek word hemi, meaning half, implying there's an intermediate level of decomposition. For this, think about organic material that still has fibers to it, but is unrecognizable as to its original source. And commonly the colors have a reddish or orange tinge to them. Then lastly, muck or sapric material, from the Greek word sapros, meaning rotten. And they have little to no fibers left and are commonly very dark to black in color. The keys to soil taxonomy provide even more specific guidance on how to make organic material separations. The determination between peat, mucky peat, and muck is based specifically on the rubbed fiber content of the organic material. So think about this in the field. And how would you make this determination between peat, mucky peat, and muck? So one of the things that the guidance tells us is that you can obtain a moist soil sample. You remove any and all live roots, as they are not counted in this test. You take the sample, you rub the sample between your thumb and your hand, or on the palm of your hand, for about 10 times with a firm pressure. And what this does is it shreds and breaks up the organic matter. And then you break open your sample and you look at it and you estimate the fiber percentage. Hand lens can be helpful when you're doing this. And if the rub fiber content is greater than 75%, then it's a peat. If it's between 17 and 75%, it's a mucky peat. And if it's less than 17%, it's a muck. Okay, so let's shift gears a little bit and talk about guidance that are given on the indicators when it comes to recording soils. All right, so let's talk about recording soil color. All right, so all colors in the field indicators for hydric soil refer to moist colors. Dry soils should be moistened until the color no longer changes. So what you see here pictured is from the indicator book, and it's an extreme example that demonstrates how different a moist sample can appear. On the left, we see it moist, and on the right, we see it dry. Something else about recording colors. In the beginning of the soil Munsell color charts, there are a couple of pages of information that provide really good guidance about the Munsell soil notation system. If you've never read them, I highly recommend that you do. There's one particular statement that has always stood out to me, and that's this quote right here. The probability of having a perfect match of the sample color is less than 1 in 100. So that means that almost all the time, you don't have a perfect match. And you may have to make interpolations about the placement of the soil in relation to the color chart. So the field indicators for hydric soils recognize this challenge in determining color in the field, and they provide guidance on how to record colors that don't have an exact match for the purpose of using the indicators, because the precision of color is paramount in making many of the indicator decisions. So for example here, if you have a color that falls into the space where that red X is at, right there. Let's say it's between the value of a 3 and 4, and its chroma falls between a 1 and a 2. And in our example here, we're going to consider the F13 umbric surface. So the color requirements for F13 is a value of 3 or less and a chroma of 1 or less. So in this case, let's say your sample is closer to a value of 3 than it is of 4. So even though it's over 3, it's still closer to 3. So then you would round your color to a value of 3, and it would meet the value requirement of the indicator. Then for the chroma, you have a color between a 1 and a 2. And it doesn't matter which chip is closer. It only matters if the chroma has exceeded a chroma of 1 or not. So in this case, because it's between a 1 and a 2, you would record that as a 1 plus. So in our example here of a soil that falls in between a value of 3 and 4 and in a chroma of 1 or 2, we would record that soil as a 7.5 YR 3-1 plus. And in that case, it does not meet the chroma requirement of F13. So the committee tells us for value, if it's in between, you round the color to the nearest chip. For chroma, if it's in between, you use the lower number and you add a plus sign. All right, so I want to talk about high chroma allowance for brighter soils. So another important aspect of color that the indicators provide guidance on is the allowance of high chroma greater than 2, but only for specific indicators. So when you have an indicator that allows a chroma of greater than 2 in its criteria, so for example, the F19 Piedmont floodplain indicator, which allows for chromas up to, but not including 4, as we see pictured here. So once you've met the layer criteria of the specific indicator, with these types of indicators that allow for a higher chroma, you can have higher chroma inclusions above your layer, and there are no restrictions upon what that color can be. So for example, if you met, let's say you met your F19 indicator, you met all the layer criteria, and then, so let's say 8 inches above that, you had a chroma of, or a color of 10YR, even 5.8, something as bright as that, it's still allowed as long as you meet the layer requirements for that specific indicator. Then let's talk about a high chroma restrictions for indicators with chroma less than 2. So for most hydric soil indicators, like the one we use the most, F3 depleted matrix, that require a matrix chroma of 2 or less within the indicator layer, the soil material above the indicator layer must also have a chroma of 2 or less, with only one exception. A single zone with a chroma of greater than 2 is permitted, but it must be less than 6 inches thick. So in this picture, which comes from the book, this profile, actually, if you just looked at it and you just compared it to F3, it would meet the F3 requirements for depleted matrix. However, since the upper portion of the profile contains a layer with chroma of 2 or more that is more than 6 inches thick, as a result, the requirements of indicator F3 depleted matrix cannot be met. Okay, so in the indicator book, there's a section that's titled as caution. So I want to highlight a couple of those areas. So a soil that is drained, in this case, in this picture that we see here, we have an area that's mapped as hydric soils. It's drained by ditches. Just realize that it may not support wetland hydrology and no longer support hydrophytic vegetation, but it can still meet the definition of a hydric soil because the phrase of the definition formed under. So in this case, the hydric soil definition, it talks about the processes that have taken place and may or may not still be occurring. So many indicators that form will persist even after hydrology has been removed. And I want to add this, and this is just my opinion based on observations. In general, I do not think that sandy indicators based on organic content will persist for long periods of time. But for fine indicators, let's say an F3, they're likely to persist for very, very long periods of time. All right, as long as the soil, this is coming from the indicators, as long as the soil meets the definition of a hydric soil, the lack of an indicator does not preclude the soil from being hydric. So in this phrase right here, the National Technical Committee for Hydric Soils is telling us there are situations when the soil can be hydric because it meets the definition, but it does not meet a hydric soil indicator. So if you think that is the case, what do? You're looking at a soil, you know it has a history of wetness, but there is no hydric soil indicator. So now what? Well, fortunately, the committee has a plan for that scenario. On page 4 in the guidance on the indicators, it says this: where soil morphology seems inconsistent with the landscape, vegetation, or observable hydrology, it is recommended to consult with an experienced soil or well scientist to determine if the soil is hydric. So the National Technical Committee for Hydric Soils, who wrote this book, emphasized the value of an experienced soil or wetland scientist because hydric soil identification is more than just a checklist exercise. It's an interpretation of complex, highly variable natural systems. We all know that real world situations can present borderline or ambiguous challenges. Sometimes hydric soil determination is not just about measuring depths and thicknesses, reading a color book, and estimating texture. It involves a deeper understanding of seasonal saturation patterns, of complex hydraulic pathways, of on-site soil formation processes, and understanding redox chemistry processes in specific soil profiles. So the committee is saying experienced experts in this field can help bridge the gap between the list of approved indicators and what the environment is actually doing. So in a situation where there is no indicator, but you think that the hydric soil definition is being met, option number 1 is best professional judgment. But what if you're in a contentious situation and option number 1 isn't getting you across the finish line? Well, there's option number 2. So option number 2 is the Hydric Soil Technical Standard, which, by the way, was just updated in May of 2025. So this is extremely labor and time intensive and comes at a considerable cost in dollars. And my purpose in this presentation is only to make it known that there is another option. The Hydric Soil Technical Standard document, it's available online. It's also on our website if you're interested in learning more about it. Basically, here's how it works. Think about the definition of a hydric soil: a soil that formed under conditions of saturation, flooding, or ponding long enough during the growing season to develop anaerobic conditions in the upper part. That's the definition. The Hydric Soil Technical Standard proves all of those elements. In essence, you're recording on-site rainfall data, you're monitoring water tables, and you're measuring anaerobic conditions. And then while you're doing all that, you're also praying that you get a normal rainfall season. So this is not a viable option for most situations, but just know that it is an option. So there's a really, really valuable piece of information that is in the indicators. It's the glossary. It's in the back of the book. Whenever you come across a term or a condition that you're not sure about, that is the go-to place to help you understand what that might mean. There's something specific that I want to highlight from that glossary. So there's a real important concept that is sometimes missed, but has to be used when you're making hydric soil indicator decisions. You have to know and recognize the differences between layers and horizons. In the glossary, the indicator horizons and layers are defined in the glossary. So horizon, here's the definition of a horizon: a layer approximately parallel to the surface of the soil, distinguishable from adjacent layers by a distinctive set of properties, produced by soil forming processes. So examples could be an AP, a BTG, an E horizon. A layer is defined as a horizon or subhorizon or combination of contiguous horizons or subhorizons. And here's the key part, sharing the properties required by an indicator. So the way I like to think about this is first, I want to know what are the horizons, the A, the E, the B, the C, whatever it might be. That helps me to understand the big picture of the soil forming processes and the distinctive properties of those horizons. And this is important because there can be different indicator requirements based on the soil horizon. So you need to know how to assign horizon labels. Then, after describing the soil horizon profiles, I like to move my thought process to layers, either grouping or dividing horizons into layers or segments that share a property required by the indicator. So let me show you an example of how this can make a difference. So in this scenario here, we're considering the F3 depleted matrix indicator, the most common indicator used by most of you on this call. We have three master horizons in this description, an A from 0 to 0.5 inches, an E starting at 0.5 and extending to 4.5 inches with 5% redox concentrations in the lower portion. And I've highlighted those redox concentrations with yellow rectangles in that lower E horizon because they were there, but they were hard to see in the picture. Then a B horizon that starts from at 4.5 and goes to 10 plus. First, this description helps me understand the big picture, the processes that are taking place. We have an A horizon that is slightly darkened with organic matter, underlaid by an E horizon, which is a middle horizon in which the dominant process is a loss of some combination of clay and iron. And this loss leaves behind a concentration of sand and silt particles. Then the B horizon below is where that material that is leaving the E is accumulating. So the B will have a higher concentration of clay and iron. So notice that we have 5% redox concentrations at the lower end of the E horizon. What's happening here in this profile is water will intermittently perch at that E and B horizon contact. And at that contact, there is a texture and structure change that slows the downward flow of water long enough to form redox concentrations along that contact. So now let's consider the Hydric Soil Indicator F3 depleted matrix. For F3, if you have an E horizon, you must have 2% or more redox concentrations. So in our description here, we have 5%. And because the starting depth of the E horizon is starting at a depth of less than 4 inches, it has a thickness requirement of 2 inches, which this E horizon meets. So if this is how you describe your profile on a data sheet, the A, E, and B with 5% redox in the E, with the depths that we've identified here, then we would meet the F3 depleted matrix. Now consider the same profile on the left, but now divided into layers instead of horizons, which is the correct way to do this for the indicators. Remember, a layer is a horizon, subhorizon, or a combination of contiguous horizons or subhorizons sharing the properties required by an indicator. So looking on the left side of the slide, when we correctly divide the profile description into layers with that key phrase, sharing the properties required by an indicator, we now have a layer I've identified as layer 3 that starts at 3 inches and goes to 4.5. Why did I separate that layer out by itself? Because this is the portion of the E horizon that meets depleted matrix criteria that requires 2% or more redox concentrations. So now, if we consider the F3 hydric soil indicator, it does not meet. Why? Because the thickness requirement of 2 inches of material that contains properties shared by the indicator is not met. So we just went from meeting an indicator because of the way we separated the horizons to not meeting an indicator because we followed the guidance of the indicators to the letter and used layers. And now it does not meet an indicator. So let me just say this too. Unless you dug a hole, you'd probably miss all of this with an auger. Okay, so let's talk about combining indicators. So it is permissible to combine certain hydric soil indicators if all requirements of the indicators are met except thickness. And the most restrictive requirements for thickness of layers in any indicator must be met. So I'm going to give you an example of how to combine indicators. So in the example that we see here, we have a horizon description. We've got a layer from 0 to 3 inches that meets the F6 redox dark surface, except it does not meet the thickness requirement of 4 inches. Then we have a layer from 3 to 6 inches that meets the S5 sandy redox indicator, except it does not meet the thickness requirement of 4 inches. But if we combine both layers, we now have 6 inches of material that meets 2 different indicators. The most restrictive thickness requirement was 4 inches. We have exceeded that, and we would now meet an indicator. Not all indicators are possible candidates for combination. For example, indicator F2, the loamy glade matrix, has no thickness requirement, and so therefore it is not a candidate for combinations. Okay. So I also want to make you aware, we got about 5 minutes left here. So I also want you to know that there is a new document that was issued earlier in 2025. It's the hydric soils of problematic conditions and altered materials. So this is a compilation of the current state of the science for problematic hydric soils. And it's a compendium, which means it's a collection of concise but detailed information. And it's like a living document that will capture the evolution of each problematic topic as that body of knowledge continues to develop. And the intent is that individual investigators and researchers will use this document as a resource to evaluate problematic settings and accurately identify hydric soils. So this is currently only available as a PDF download from NRCS. We do also have a copy on our website at hammerenv.com under educational materials and resources. So here's a look at the table of contents. You can kind of get an idea of a list of the broad spectrum of items that are covered in this particular document. It is completely free and available for download. Okay, well, thanks for being here with us today. Just a couple more things. What's next? So what's next is we'd like to hear from you. What training topics would you like to see us cover? Are there specific indicators that have been a thorn in your side or trouble for you? If there are, please let us know what they are. So we have another webinar that's scheduled for January the 27th at 10 a.m. Hope you're able to join us for that. There is an early bird discount for VOP members. An early bird discount for anybody who registers, and there's always a discount for VOP members as well.